Hello and welcome to a brief presentation on the concept of Bernoulli's principle, which you may have heard of, which is encompassed within the realm of fluids. And Bernoulli's principle, first and foremost, is really just a restatement of the conservation of energy, which states that when no external force is present, energy in a system must be conserved. And specifically, the type of conservation of energy that we're talking about in this concept or this example is describing what changes in a fluid when you have variations in the height of the fluid, the velocity at which the fluid is moving, and the pressure caused by the fluid. So, first and foremost, to derive this principle, we're going to start off with the conservation of energy equation, and more specifically, the work energy theorem, which affirms the fact that work changes the energy of a system, or in reverse, the energy of a system is changed when work is present. So we could denote that as, let me switch colors here, we could denote that as W, work, is equal to change in E, or total energy. And we're going to substitute in values on both sides of the equation now. So we know that work is equal to applying a force across a distance. So we could say that this is equal to force times distance. And here we could think of the distance as the height across which the fluid is being moved. And if we have a change in energy on the right-hand side of the equation, we know that the change in energy equals the energy of the system at its final point minus the energy of the system at its initial point. And here, we could assume that energy is some combination of potential energy, which is caused by position, and kinetic energy, which is caused by motion or some pre-existing velocity. So we could write this as delta E is equal to the final potential energy plus the the final kinetic energy minus the initial potential energy minus the initial kinetic energy. So this is really just saying that UF plus KF minus UI plus KI is equal to change in energy. It's a lot easier when you write it out in that format. Okay, so now we could substitute in values on the right-hand side of the equation. So we're just going to keep the same thing on the left-hand side. We're going to say that force times distance is equal to, okay, now when I look at UF, my final potential energy, well, won't my final potential energy just be equal to mass times acceleration due to gravity times the final height of the system, which we could call 2, or the final height of the liquid? And similarly, the final kinetic energy is equal to 1/2 m times the final velocity, which we could call v2 squared of the fluid. And then we could just do the same exact things for the initial potential and kinetic energies. So we could subtract mgh1, and we could subtract 1/2 mv1 squared. Okay, so now what can we do with the left-hand side of the equation? Well, we know that if we're talking about fluids, there's probably going to be some relation involving pressure, force, and area. And remember that we can achieve pressure, or more specifically, we could achieve a change in pressure when we apply a force over some distance. And more specifically, when that distance is expressed in area format. So we know that, let's see if we could extend this over here. We know that, let me switch colors, pressure is caused by a force divided by an area. Okay, so then that implies that a force, which we have on the left-hand side of the equation, is equal to the product of pressure and area. Well, that's rather convenient because now we could substitute in, actually, you know what? Let me make this change in pressure, right? We're causing a change in pressure when we apply a force over an area. Okay, so now I could substitute in F is equal to delta P times A. So let me do that now. Let me switch colors for that. So delta P times A times D is equal to, and then we're just going to keep the right-hand side of the equation constant. Okay, well, what is area times distance equal to? Well, if I have a cross-sectional area and I extend that cross-sectional area across a distance, I achieve a volume, which is equal to P. So now, essentially, what I get is delta P times volume is equal to the right-hand side of the equation, which I'm just going to rewrite here for ease of reference. mv2 squared minus mgh1 minus 1/2 mv1 squared. Okay, now what would happen if I divide both sides of the equation by volume? Well, let's see. If I do that, I get delta P by itself, which is very convenient. Looking over here, mgh2 divided by V, well, we also know then, let me do this off to the side somewhere. We know that our fluid's density, rho, is equal to its mass per unit volume. So if on the right-hand side of the equation, recognizing that I have mass in each one of these terms, if I divide that by volume, I'll get the density of the fluid. So now, applying that logic, then delta P, my change in pressure, is equal to m divided by V times G times H2, or simply rho GH2, plus 1/2. Now, okay, wait a second. If I divide my mass here by volume, I also get rho. So half rho V2 squared, minus, same thing over here, dividing mass by my volume, I get rho GH1, and then same thing over here, minus half rho V1 squared. Okay, so now let's see what would happen if I rewrote the change in pressure as being equal to the final pressure, which we could call P2, minus the initial pressure, which is P1, right? That's just the definition of the change in whatever quantity. And I'm just going to rewrite the right-hand side of this equation. Rho GH1 minus 1/2 rho V1 squared. Okay, perfect. Now, just rearranging terms so that I could get each one of the first pressures on one side of the equation, and then each side of the second pressures or the final pressures on the other side of the equation with all the other first and second terms, I come up with a format that looks like this. P1 plus rho GH1 plus 1/2 rho V1 squared, right? So this is all my initial terms, is equal to P2 plus rho GH2 plus 1/2 rho V1 squared. And there you have it. This is the definition of Bernoulli's equation, which relates the velocity of a fluid, its pressures, and the height at which it sits. And of course, that's presupposing that you know the density of the fluid and the acceleration due to gravity. And once you know a sufficient number of these terms, you could solve for all the rest. And really, if I could draw a picture of this, this is describing something that would look approximately like this, where you have a pipe of some sort. You have a cross-sectional area. And then you have a change in the pipe, a change in height. So we could say that the height from the center, oops, let me get a line for this. Perfect. Let's say that. Call this height and that height, respectively. We could call these H1 and H2, and call this H1, call that H2. And then if we have some initial and final velocities with which the liquid is moving, which I could draw right here using vector notation. Okay. Call this V1 and V2. And then, in addition, each one of these openings to the pipe, for example, has some pressure values, which I could call P1 and P2. So as you could see, at each end of the pipe, and indeed throughout as well, we have a height, a velocity with which the fluid is moving, and some sort of pressure. And you might find that it's often the case that these two pressure values are equivalent, and that they're equal to atmospheric pressure. Specifically, that will occur if the liquid in the pipe is being exposed to the environment, and thus is at atmospheric pressure. So here you go. You have a derivation of Bernoulli's principle and Bernoulli's equation with an example drawn out. Thank you guys for watching, and I will see you in the next one.